Good morning. It's great to be here. I am Ivan Krstić. I head security engineering and architecture at Apple. I wanted to thank the organizers especially for letting me do this 2.5-hour long presentation, so get comfortable. No, but it will be about an hour in 30 minutes, so I will move very fast. Blink and you will miss it. All right. Yes, great. So what I want to do today is walk you through how we have thought about security and privacy of modern cloud AI and the threats that our users face and the steps that are required to address them. And then I'm going to discuss how those considerations shaped our private cloud compute design, first on Apple Silicon, and how we then just recently expanded it to Google Cloud while maintaining our security bar. So we're going to dive right in. To orient ourselves, you all know this, but with traditional cloud AI, a user's device will send the prompt to the cloud service. The service is effectively opaque to the user. After some processing, a model response is returned to the user's device. And the security properties here leave a lot to be desired. Any security and privacy guarantees are difficult to verify and enforce. It's difficult to provide runtime transparency to conclusively show what software was running or how it's being used. And finally, it's hard to enforce any kind of strong limits on privileged operator access. Now, researchers agree that Apple builds the most secure consumer mobile devices in the world. We keep data on device as much as possible with industry-leading defenses that are constantly scrutinized by security researchers. So it shouldn't surprise you that when we first started assessing cloud AI, we wanted a much stronger security model than what existed in the industry. And that model is to make cloud AI processing an extension of the security and privacy of your iPhone. We want to operate on behalf of the user and minimize trust in everybody else, including the cloud AI service itself. So let's take our standard cloud AI model and flesh it out so we can actually start thinking about the entire inference pipeline. First, we have to consider any front-end and middleware services that are handling the request. Then we have the inference pipeline itself, as well as the privileged operators that are able to access it, and its entire software supply chain. And finally, any observability, analytics, or data warehouse systems that might be storing data produced by the inference pipeline. All of this is managed by the service operator, and we need to consider their infrastructure decisions as well as attackers operating from inside or outside their network. The service then sits on top of the cloud service provider and their hardware supply chain. So essentially, every single part of this is an attack surface, creating a tremendous number of potential threats that can impact the user. To help formalize our thinking on securing these systems, we developed a simple coarse-grained framework that classifies cloud AI in 4 broad security levels. What we've discussed just now was level 0. Level 0 has a large, complex, and opaque software supply chain. It uses shared inference pipeline that concurrently operates on data from many users. It enables privileged access for the site operators for debugging, and any data retention and use policy is just that, a policy. There is no inspectable technical enforcement of how data is retained and used. So level 0 accepts operation with a substantial and very broad range of heterogeneous threats against user data. To move to level 1, we need an auditable, high-security, hermetic inference pipeline. Using a measured boot flow that covers all the runtime code, the systems within the inference pipeline need to be verified against a tamper-proof ledger, so we can audit both the code itself and any privileged or observability access to the system. And the inference architecture itself needs to be built with resilience in mind, ensuring that it doesn't retain user data beyond what's strictly permitted. At level 1, we get a much better picture in terms of the trusted components. Our users still have to trust the AI service front end to route their requests to a secure pipeline, and they still have to trust the service provider, the service operator, the cloud service provider, and the hardware supply chain. But a well-designed level 1 cloud AI system can limit the risk from all of these other threats. But this still poses substantial risks to user privacy. An operator could covertly deploy modified software that implements different data retention practices than claimed publicly, or perform user-targeted substitution, where particular users are targeted with different software or hardware, or manipulate callouts to leak specific data to external services or tools like web search. So to move to level 2, we need to add verification of the cloud AI service and the underlying cloud provider. We do this first with verifiable transparency. Software images are published for inspection, the system attests to the software that it's running, and transparency log inclusion is enforced by the client software. But we also need non-targetability. Service access must be via anonymizing relays, and authentication must use anonymous tokens, ensuring the service operator cannot target specific users or content. And finally, we need call-out transparency, which is to say that calls outside of the inference trust boundary must be inspectable by the user. It's important to emphasize something about level 2, which is that we believe non-targetability is not optional. It's a critical component of this level. And that's because it raises the bar on attacks by ensuring that an attacker must compromise the entire system to get data of interest, rather than targeting just one node. So this places scalability limits on hardware attacks, forcing them to be implemented at scale, and it ensures the data leakage, for example via side channels, doesn't provide data that is attributable to a specific user. If we can address all of these threats, we can minimize trust in the service operator as well as some of the trust in the cloud service provider. Last, to reach level 3, we have to defend against advanced adversaries. These adversaries are well-funded, may be state-sponsored, and they can carry out sophisticated attacks. And that includes side-channel attacks, where they can become co-resident with an otherwise hermetic workload and can then leverage side channels to extract user data, as well as hardware supply chain attacks, where they can compromise the root of trust via certificate misissuance. If we're able to meaningfully protect against all of these threats, we rise to level 3, what we call frontier security and privacy, which we can accomplish by providing side channel resistance through limiting co-resident code and by providing hardware supply chain auditability and redundancy. So if we handle these threats, we can finish minimizing trust in both the cloud AI service front end, as well as the cloud service provider and their hardware supply chain. Now, even with all of these steps, we should still be clear about the risks that remain. All software will have bugs, and exploitation of those bugs has the potential to allow an attacker access to some user data. In addition, hardware defenses can raise the cost and detectability of an attack, but they can't prevent it outright. So level 3 systems have to be designed to minimize and recover both from complete fleet compromise for a short period of time due to software exploitation, as well as persistent partial compromise due to a hardware supply chain attack. And designing for that really requires thinking carefully about what data is present in the AI system and at what time. And finally, abuse monitoring and mitigation remains quite sophisticated and challenging with level 3 systems. So that's the framework for how we approach the problem. And now we can turn our attention to private cloud compute on Apple Silicon and how we ensured that it met all of these requirements. First, we'll build level 1, the world's most secure and private system for stateless AI inference. This starts with the PCC node itself, which is our custom Apple Silicon server. It leverages the foundations of iOS, as well as a set of custom cloud extensions designed with privacy in mind. And finally, we built our inference engine to provide stateless inference at scale. Now, the PCC node is the atomic unit of our trust boundary, and it's designed to ensure that personal data resides within the trust boundary and that it's not retained, other than the special case of the KV cache, which we'll talk about in a moment. Building this wasn't as simple as just running iOS on a server. In addition to the decades of investment that we have placed in iOS security, we also brought a range of new features and technologies to the system, and we'll cover a few of them. The first step in the lifecycle of a PCC node is the measured boot flow that takes us all the way to its hermetic runtime. We start with immutable code in the silicon as part of our SOC root boot chain, which measures and records all the code that can execute in the system until we finally seal it and prevent the loading of any additional code. Once the system is up, it's time to perform inference. We isolate all of our data processing to minimize and contain any potential compromise. All processing for us starts in CloudBoard, which handles and demultiplexes incoming connections and ensures that we can use the appropriate attestations to exchange keys. Then it hands off to isolated process per request instances that handle the actual decryption of the request, as well as the initial processing of the request data. That finally hands off to our inference engine, which is periodically recycled to minimize the amount of time that any data can stay resident in the system. Implementing an inference engine for a secure and private service presents some unique challenges. One of these comes in the form of prefix caching. On a traditional AI system, you would simply build a cache of previously presented prompts, but with stateless inference, we need to ensure that one request cannot influence another and the data isn't retained. So we separate system prompts from user data, and rather than letting a node discover shared prefixes automatically from traffic, we deliver a tree of system prefix data to our PCC nodes ahead of time to seed the initial set of cached KV content. Then, as a user makes a request, we maintain their state encrypted with a per-user key. And so this allows us to continue to process requests without having to recompute previous turns, but it also ensures that a user's data is cryptographically unavailable to us outside of a live request. And of course, we need to be able to operate all of this without any privileged runtime access. So we had to build specific filter mechanisms for metrics, logs, and crash reports, as well as custom diagnostic tools so that we can actually empower both our observability systems and our site reliability engineers to operate the service while ensuring we have multiple levels of review for all data that leaves the trust boundary. That just gets us to level 1. Now let's take it further and make the system non-targetable and verifiably transparent. Verifiable transparency starts with end-to-end attestation. The PCC node must present its attestation to the end user's device, which verifies that the software measurements which are present in a public append-only transparency log. Security researchers can use the virtual research environment toolset to access that same log and download the software corresponding to each release. And this allows the broader privacy and security community to verify our claims and look for bugs and flaws in our implementation. The attestations start from the hardware identity, which is rooted in our secure enclave. Every secure enclave has a unique identifier that is securely generated and fused into the silicon during manufacturing. From this, we're able to derive what we call the data center identity key, which is a permanent identity that's attached to that piece of silicon that we use throughout PCC. The secure enclave signs the full system attestation using that data center identity key. And this captures the full software stack. The boot register that covers the underlying operating system, a set of software sealed hashes that cover the application software running on top. And so those measurements, along with the rest of the necessary collateral, form an attestation bundle that a device can use to verify exactly what is running on the PCC node that it's talking to. Each attestation bundle corresponds with a specific release digest, and PCC infrastructure generates an inclusion proof that the release digest is present in the transparency log, which allows efficient validation by the end user's device. Now, we use transitive trust to allow us to perform load balancing just in time while also ensuring that we don't weaken any of our verification in the process. The way we do this is that the proxy node commits to a particular revision of the transparency log as its view of that log, from which it will perform all attestation validation. It includes that in its own attestation, which it provides to the client device. And so this way, the view of the log that is seen by the user is actually guaranteed to include all software that processes that user's request. This provides verifiable transparency, but we also need to ensure non-targetability. And so for this, we bring in 2 more components, an anonymous authentication scheme as well as a third-party privacy gateway. Our authentication process involves 4 steps. The first is to issue anonymous one-time tokens to the device using RSA blind signatures. The device redeems those tokens to issue inference requests, and along with the response, it also gets a cost token, which is essentially a receipt of the cost of that inference request. The device then aggregates these cost tokens anonymously, communicating through an oblivious HTTP relay to our cost aggregation service, which returns a range of cost denomination values that sum to the total that needs to be replenished. And then finally, when it comes time to fetch additional inference tokens, the user's device can include those anonymous cost denominations, which will replenish the user's quota. So this is a lot of work to ensure minimal data leakage. We cannot link the cost of any individual request to the replenishments that we will ultimately issue. In addition to the anonymous authentication, we also need to ensure that access to other services, such as world knowledge, cannot become a privacy leakage vector. And we do this through the request execution log. Anytime a PCC node wants to access an external service to fulfill a request, for example, accessing the world knowledge database, it includes the query terms of that request in a request execution log. And then our users can verify those terms by looking at the Apple Intelligence report on their own device, ensuring that the search terms were reasonable and valid. Of course, to make all of these steps useful, we need to pair them with tools that allow security and privacy researchers to verify the system. And that starts with our virtual research environment, which allows anyone to run the PCC inference software in a virtual machine right on their Mac. It also includes the supporting source code and documentation, just as you would expect. So with all of this, it's now time for level 3, protecting against advanced threats such as side channel and hardware supply chain attacks. For PCC on Apple Silicon, we have a naturally side-channel resistant design. Our verifiable transparency covers the entire SoC. We have exploit isolation techniques that limit within SoC side channels, and we continue to follow the state-of-the-art of evolving research on network and power side channels to ensure that we've mitigated those attacks. We also need to consider how we secure our root of trust. Our goal is simple. Admitting bad PCC nodes to the fleet should require a severe multi-party breach. And we accomplish this by using a provisioning ceremony that evaluates a range of evidence about the hardware's authenticity and integrity. And that evidence then allows an independent auditor to review the process and ensure compliance. The ceremony we have puts each chassis through a sequence of validation gates. We start with manufacturing, confirming the node was genuinely built by Apple with a valid paper trail. Then we validate the physical chassis and its location. Next, we check the chassis is still sealed. Then we confirm the software is inspectable and the silicon is fused correctly. And finally, we validate the node identity. Only once a chassis clears every one of these gates do we issue it a certificate allowing it to join the PCC fleet. All right, let's take a breath. Hope you caught all of that. As you can imagine, it was a formidable challenge to expand this architecture to Google Cloud. And so next, I'd like to talk about how we accomplished that. The first and most important thing you have to know is that we were unwilling to lower the level of security or privacy at all during this expansion. But the principal challenge of the expansion is to deliver a secure system that can minimize trust both in hardware vendors and the cloud provider. So how do we approach level 1? For PCC on Google Cloud, we started with Google's attested container optimized OS, or ACOS, running in an Intel TDX CVM. This is a hardened image, it's designed for zero operator access, and it ensures only attested code runs. And this image is open source and auditable. Now, what's hard to guarantee here is full attestation coverage. In other words, that the system is truly hermetic and doesn't have a path to load arbitrary code. PCC on Apple Silicon used iOS's existing signing mechanisms, but the Linux ecosystem is quite diverse and presents a number of new challenges. So working in close collaboration with Google, we ensured that ACOS was designed to boot to a truly hermetic runtime. And this included ensuring that instance metadata pre-declares all containers and their hashes, a boot flow that loads only the specified container and measures it into a runtime register, a new eBPF Linux security module that restricts execution to only known binaries, and carefully monitoring any place where we had both a read-write file system and a shell. We also had to think carefully about how we protect attestation keys. On Apple Silicon, the Secure Enclave provides integrated key management and attestation capabilities, and this ensures one very important property, which is that attested keys cannot be exported or exfiltrated. But for PCC on Google Cloud, we collaborated with Google to build a key management confidential virtual machine. So this is an independent TDX CVM running on the same host in a separate isolation domain, ensuring that a compromise of the inference CVM would not allow exfiltrating keys. When it comes time to do inference on Google Cloud, we ported some of our key technologies to Linux. This included CloudBoard to provide attestation and request handling, as well as our techniques for auditing logs and metrics. We also adopted a number of Linux native technologies, and we ported the inference engine to run our Apple Foundation models. So with that baseline set, let's reach for level 2. When it comes time to route a request, we use the same transitive trust techniques as with PCC on Apple Silicon. But this time, our proxy validates the attestation of Google Cloud nodes. Expanding our security research program to cover this new hardware presents a number of unique challenges. The hardware is expensive, it's hard to access, yet it's necessary to verify transparency. Validating that the attestations match particular firmware requires reproducing golden measurements on live hardware, and encrypted firmware means that the hardware is needed to verify runtime behavior. And so to address these, we will be providing access to real hardware for qualified security researchers. Finally, let's push all the way to level 3. An observation we made is that confidential VMs are not on their own sufficient to protect against sophisticated attackers. The key challenge is side channel resistance. Confidential VMs leave data open to side channel attacks from the host. And this has been seen repeatedly in the academic literature, including TDX-Ray, which is able to recover a user's LLM prompt from a single trace. But one of our key insights from PCC on Apple Silicon is that most side channels become unreachable when there is no co-resident workload on the system to act as a launch point for attacks. Therefore, we have a hard requirement: attest the entire system, not just the confidential VM. So PCC on Google Cloud uses whole host attestation. The host is also running the same attested container optimized OS as the guest. The system boots directly to a single application CVM plus the key management CVM, and the system will reboot before loading any other CVM, just like the guest. The host runs only attested code and has no privileged operator access. Our boot flow leverages multiple roots of trust. We start with the Google Titan root of trust for the host boot, which records measurements of the BIOS, the host firmware, the host OS, and the hypervisor. And the contents of the guest workload and the key CVMs, as well as our application containers, are all covered by TDX. The last step prior to lockdown is to record the measurements of the confidential mode GPUs. And the measurements from each root of trust contribute to this whole host attestation. And this is a key point for us. These layered attestations also provide redundant roots of trust. Hardware supply chain resistance is another crucial property, and with PCC on Apple Silicon, we accomplish this through the use of an extra auditor. For PCC on Google Cloud, as we said in the beginning, it wasn't enough just to minimize our trust in the service provider, we must also minimize our trust in the hardware vendors. And so we believe a level 3 Cloud AI service should have multi-party control over the root of trust, in this case by using multiple vendors together. In our case, the multiple roots of trust include the Google Titan for the boot chain, as well as Intel TDX for the CPU. For the GPU, we rely on NVIDIA's root of trust alone because that component on its own doesn't have the ability to independently exfiltrate user data. Of course, the firmware measurements of all of these components are included in our transparency log, and just like the Google Cloud hardware identities, which ensures that attacks on the hardware supply chain can be detected. Ultimately, it just should not be this hard for a Cloud AI service to operate at level 3. Most deployed systems today target at most level 1, with many unable to achieve it. Systems from large companies often have no transparency or partial transparency. Systems from smaller vendors often skip non-targetability, which we consider a hard requirement. And what's more, current confidential computing primitives on their own don't enable level 3, which puts a ceiling on what most commodity providers can offer for Cloud AI. In fact, we've analyzed a number of Cloud AI systems based on entirely the published security information, and we've tried to do that as a straightforward reading of the information they themselves publish, and this is our best current assessment as of this moment. We believe that PCC is the only system that meets level 3 today, and that no widely deployed system today meets level 2. This has to change. At Apple, we believe privacy is a fundamental human right. And we believe that the immense promise of AI will be fulfilled only if we build systems that are worthy of our users' highest trust. And this is why, since the very first version of PCC, we have been publishing tools and code and documentation, tremendously detailed technical documentation, hoping to inspire more work like this in the industry. The work ahead of us is difficult, but I hope that the people in this room will be part of the tide that lifts all boats, and that we will help deliver a more trustworthy AI future for all. Thank you for having me.